Our next speaker is Adrian Notarantonio. I practiced this. And he's going to speak on effective algebraicity for solutions of systems of functional equations with one catalytic. It's good at the end. With one catalytic variable.
Okay, so thank you very much for the introduction. And before starting my talk, I would like to thank the organizers for this very nice organizations. So I am a second-year PhD student in France, and I will be presenting a joint work with Sergei Yurkevich, who is in the audience. Just to mention that we are both two students of in Boston. And so it is a rather long title, so I will try to explain each word of this title. But let me first try to introduce functional equations with one catalytic variables. And to do this, I will use an example which has combinatorial origins. So this is what we call a three constellation, and it can be seen as bicolored planar maps with some additional constraints on the degree of the faces. And in such a context, usually appear such functional equations. So the objects are the following. There is a principal variable called t, and there is also a variable u, and then there are two series, so f of tu and f of t1. And let me try to explain in what context does such an equation appear. So here I am interested in enumerating such objects, for instance. So I introduce the sequence an, counting the three constellations with n purple faces. And what is usually done in enumerative combinatorics is to refine the enumeration of interest to make the study easier. And so this is why I introduced the sequence A and D, which counts the three constellations with n purple faces and outer degree 3D. So algebraically, in the first case, we have a univariate formal power series GT. And in the second case, we introduced an extra variable, which is called catalytic. So this is why I am talking about one catalytic variable. Well, the thing is that when you fix the number of faces, you cannot have an infinite degree. Then the coefficient of this series are polynomials in the catalytic variable. And now the good property is that the specialization to u is equal to 1 of the function f is just the initial generating function g of t. And what I am interested in is in the nature of the series that appear in this slide. And there is, well, many results saying that this series is an algebraic function. And this means that there exists a relation that annihilates the function g with polynomial coefficients in the principal variable t. So this is, in particular, a consequence of a beautiful result due to Mireille Buscamello and Arnaud Jehan, which says that when I denote k a field of characteristic 0, and then when I introduce what we call the discrete derivative operator, which can be seen as just a shift on the coefficients of the series f, then for any discrete differential equation, which has the following form, and which has a fixed point nature in the series f, then there exists a unique solution with polynomial coefficients in the catalytic variable. And moreover, this solution is an algebraic function. And starting from such a result, what is usually done is to compute a witness of the algebraicity and to deduce properties so on the sequence of on the initial enumerations, like an asymptotic growth or an exact formula if it is possible. And well, in the literature, there exist many contributors that studied this question of computing annihilating polynomials. And in this talk, in the title, there was this word system. So now I will be interested about the case of systems. And indeed, in the literature, there are some examples of systems of discrete differential equations. And the question is still the same. Can we classify the nature of the series F? And then can we compute eventually a witness of this nature and deduce properties on the sequences and some properties on the combinatorial objects? And indeed, there exists a very deep result in commutative algebra, which is due to Popescu in 1986, and which implies that all the series that are considered, and especially the specialization, is an algebraic function. But the fact is that the proof is a priori highly non-constructive, and so there does not exist any algorithm for computing an annihilating polynomial. But in the case of linear discrete differential equations, there is a paper by Manfred Bochachel and Manuel Kauers in 2019, which says that indeed we have the algebraicity, and this was already a consequence of Popescu, but they have an effective proof, and so by following their proof, it yields an algorithm, and so we can compute such witnesses. But still, in the literature, there exist many examples dealing with these systems. And so at some point, with Sergey, we were asking ourselves, maybe there is something to say about these systems of discrete differential equations, and maybe there exists an effective proof also, which yields an implicit algorithm. And this is, indeed the case, and this is our contribution to this edition of FPSAC. So let's have a look at this result. So first, let me mention that it is still included in papers of Popescu and Swan, but in the end, our proof is effective, and so there exists an algorithm for computing annihilating polynomials for the specialized solution. And here, the only thing that is new is the fact that we deal with systems. We have this nabla operator, which just says that we can consider every discrete derivative operator, so every iteration on any of the series that are considered in this system. And if the equations are in a fixed point type, like here, then there exists a unique vector of solutions whose components are algebraic functions. And so let me give you some intuition about this result and about our method. So here, I take an example from the literature, and I take the numerator of both equations, so I multiply by u minus 1 in order to deal only with polynomial functional equations. And now I denote by E1 and E2 two polynomials such that when I substitute f, g, and the specialized solution in these polynomials, then I obtain this system. And what is usually done in this field is to take the derivative with respect to the catalytic variable. So this is a common idea. And in such a case, with the chain rule, we obtain the following linear system with now the extra series del uf and del ug. And the observation is that, if there exists a series u of t with positive exponent in t, because we are composing series, so in order to make them well-defined, we want positive exponent in t. So if there exists a series which annihilates, which cancels, the determinant of this matrix, then there exists a linear relation between del x1, the columns del x1 and del x2, and by this relation, there exists a relation between del x1, del x2, and del u, and so we'll have a root or a solution of the determinant of the matrix obtained by gluing the columns del x1 and del u. So this gives an extra equation. And as we are dealing with algebraicity results, what we usually want to do is to create as many equations as unknowns. And with a little bit of optimism, then we can hope to have finitely many solutions. And then eliminating all variables but the ones of interest yields an annihilating polynomial. So this is the usual strategy. And in the general case, it works the same. We take E1, En, the numerator equations, and we differentiate then with respect to U still. And we introduce the two polynomials det and p, where P is again just the replacement of the column del xn by del u in this matrix det. And the observation is exactly the same. If there exists a series U which annihilates, which vanishes the equation det, then there exists also this relation, this extra relation. But as I told you, here the final goal is to have as many equations as unknown, and it is not the case a priori here. So there is, again, one thing to say. And this is why, well, I duplicate the system here. So I introduced new variables, U1 until U and K for the NK distinct solutions in U of this equation. I also duplicate all the variables associated to the series which depends on U. This is the usual trick used in the article of Buscamello and Jeanne. And then there exists, well, by counting, as many equations as unknowns. And as I told you, well, the hope is that the ideal generated by this system SDUP has finitely many solutions. But the thing is that, well, this is only if that U has NK distinct solutions in U. And there are some examples in the literature where it is not the case. So here, for this system, we obtain this polynomial det, and it is, well, straightforward to see that there exists only one solution which has positive exponent in T, because the equation is of a fixed point type, so it's, well, straightforward. But NK is equal to 2, so there is a problem which, with what I was saying before. And so we should understand how to create more equations to this equation that U is equal to 0. And the way we do it is by starting from the initial system and then using some symbolic deformation. So we are going to introduce alpha, beta, two relatively big integers, and also an extra variable epsilon, which is called the deformation parameter. And by considering now this new system, here the goal with the alpha is to push far away in terms of valuation in T all the degeneracy of the initial system. And so now there exists also a solution to this system just by extracting the nth coefficient in T. And if we can prove the algebraicity for the new series, then by specializing epsilon T0, we will have the algebraicity of the initial solutions to the initial system. And from now on, I will denote by E1 until En the numerator equation of this deformed system. Okay, so let's move on. We have first this lemma, which is a consequence of our symbolic deformation, and which says that indeed there exists as many solutions as expected. And this is done briefly by computing the first term of det, and then by using a Newton-Peters algorithm. And then when we have these NK distinct solutions, then it remains to glue all the series in a point that we will denote by P. So we really duplicate all the series, all the points U1 until UNK, and we glue them in a unique point, P. And the lemma is now the following. If the Jacobian matrix of the duplicated system is invertible at the point P, then, well, by considering the set of solutions which cancels this duplicated system SDUP minus the set of solutions which cancels the determinant of this Jacobian matrix, then we will have an ideal which vanishes at the point P and which has expected dimension 0. So this is a consequence of the Jacobian criterion in algebraic geometry. And so now the goal is to show that this determinant is not 0 at the point of interest. And just to mention that in the end, it's just about using some tools from effective algebraic geometry. Okay, so let's move on and see the shape of this duplicated matrix. So we have this, sorry. So we have the property that up to some elementary operation, this Jacobian matrix at the point of interest is an upper block triangular matrix. So to show the invertibility, we will just study all the blocks located on the main diagonal. And there are two types of blocks. The first are the green ones, and then there is this blue one. So in the first case, we show that the valuation in T of the determinant of the green, matrices is finite, and this is due this is proven with heavy computations by hand. Like we really compute explicitly the valuation. And in the second case, we show that the determinant of the blue matrix factors mod T to the alpha with this beautiful form. So we have a van der Monde matrix, as we know that we have a van der Monde determinant, sorry. So as we know that all the UIs are distinct, then it will be non-zero. And we have this polynomial H, which depends only on T and epsilon, and whose degree is independent of alpha. So in the end, we will indeed have the fact that this determinant is not equal to 0. And again, this is a big extension of the ideas of Buscamelo and Jeanne, but it is not at all straightforward. And so let me summarize the algorithm, starting from a system of discrete differential equation. Then we define the polynomials det and p. We duplicate the system with sdup. And now it is enough to eliminate all variables. So here I put a z0, and z0 would be, for instance, the variable associated to, f1 specialized at a point. So this is the algorithm, which is a consequence of our effective proof. And now to summarize, we have seen that solutions of systems of discrete differential equations are algebraic series. And we have so now an algorithm which computes any of the specializations of interest. So now from this polynomial, we can deduce more properties of the initial sequences. And a natural perspective is what about the case of more catalytic variables? And in this case, it is still covered by Popescu's result, but in theory only. So we don't need, we don't know any effective proof and any algorithm. So this is a potential perspective. And just to spoil a little bit, so we are currently working on making more efficient strategies, on designing new algorithms which avoid this duplication of variables argument, which is usually very nice for showing some algebraicity result, but in practice it's usually an overkill. So we are currently working on it, and it will rely mostly on the use of effective algebraic geometry and Grobner basis. Okay, so thank you for your attention.
Questions?
Yes.
I would like to ask, in your new efficient algorithm, it's still a bit slow, but do you identify some parts of it that can be massively parallelized?
Some part of the algorithm? Sorry, so the question was to identify some part of our new algorithm that could be parallelized?
Yes.
So if it relies on the use of Grobner basis, there are some current implementations, like in MSolve, that uses this parallelization property on multiple threads, etc. So at this level, of course, it could be parallelized, but the algorithm is not designed to be parallelized, intrinsically. It's more a consequence of the good implementations of Grobner basis algorithms.
Okay, thank you.
You're welcome.
Other questions?
Ah, yeah.
Est-ce que les fonctions f, elles sont, au final, est-ce que ça montre qu'ils sont différentiablement finis?
Okay, so the question is, does the algebraicity implies the fact that the series are definite or holonomic? And indeed, it is the case. It is always the case. Algebraic functions are definite functions.
Other questions? If not, let's thank the speaker.